Thank you very much, Jan. I think you can see my presentation now. So indeed, I'm Philippe Nimmegeers. I'm a postdoctoral researcher at the University of Antwerp since November 2020. Before I was active in industry for 2 years. And before that, I was actually at KU Leuven, working in chemical engineering and model-based optimization of chemical and biochemical processes. So now I'm active actually in 2 research groups. First research group I'm active in, and at which I have conducted my research related to this topic, is the iPRACS research group, which my colleague Lukáš presented a few weeks ago at the Capture. And I'm also active in the EnvEcon research group, which is part of the Faculty of Business and Economics at the University of Antwerp, in which then the focus is more in the study of the interaction between environment and economy, and which our expertise consists mainly of doing techno-economic assessments and methodological developments for the assessment of sustainability in different applications. Now, today we're going to talk actually about recyclability, and something we quite often see in our daily life or nowadays is our labels like, okay, this is 100% recyclable. And the question is actually, what does this actually mean? This 100% recyclability is quite vague. It's quite often a branding strategy. And if we think about plastics quite often, and we see how they are stored and recycled, or we look at bales which result from a mechanical recycling, we see that actually recycling of plastics is quite complicated. And a lot of attention is spent currently when they are assessing the recyclability of plastics, is spent on actually energy requirements which are needed to recycle plastic. It's more on energetic or enthalpic considerations that are being done. While actually we all know that the complexity, the entropic nature of plastics or plastic waste is actually more influencing this recyclability question. And that's actually the thing that we want to address during this talk, using entropy to quantify the recyclability of plastics or plastic waste. Now, entropy is a quite complicated concept, and when you mention the word of entropy, some people might think about their classical courses in thermodynamics, in which you think about how can spontaneous processes occur. There's a concept of Gibbs-free energy, and we know that spontaneous processes, well, they occur when you have a minimal enthalpy, minimal energy, and maximum disorder or entropy. So entropy is actually a measure of disorder. Now, another topic, another concept that people might know is a concept of Boltzmann entropy, in which we actually try to describe actually the number of microstates in molecular arrangements that can actually describe or constitute a certain macrostate. And such equations as the Boltzmann equation, in which a logarithm of a certain probability of a certain macrostate occurring due to some microstates, is depicted. Now, what we are doing actually, when we're thinking about how to quantify the complexity of plastics and the recyclability of plastics, was grabbing back to statistical entropy, which originates actually from Shannon's entropy, information theory. And around 20 years ago, Helmut Rechberger and Paul Brunner actually proposed to use the concept of statistical entropy in the field of quantifying the complexity or the capability of processes to dilute or concentrate certain streams in a certain substance. So the focus was actually in purifying substances, purifying streams, or actually converting waste to energy and assessing processes in that frame. Now, the main drawback of that method is that it mainly focuses on one substance, and that is the thing that Alexei Parkhomenko 2 weeks ago presented actually at Capture, in which they actually look at multi-component systems, as for instance the car example that Alexei presented 2 weeks ago. Now, we actually looked at it at a different point. We looked actually at plastics, and we used this framework of Alexei Parkhomenko and co-authors to apply this framework of multi-level statistical entropy to addressing the plastic recyclability question. Now, what does this mean and how can we do this? For this, we actually have a simple toy example, which you actually have a plastic bag which is filled with 2 types of components. A component which consists of two materials, and these two materials are linked together in a different manner, but the substance composition is exactly the same. Now, if we apply then the concept of statistical or multi-level statistical entropy analysis to this, multi-level statistical entropy analysis looking at entropies at different levels of the system, and we want to study how these components influence actually the complexity or the separation complexity of the system, then we see actually that these two components have the same entropy because the substance composition is the same. So what does this tell us? Although it's a very interesting method, this multi-level statistical entropy analysis to study, for instance, resource effectiveness, etc. But if you want to apply it to the recyclability question of plastics, we're missing something. It also depends, of course, on the system definition, etc. But if we define our system in this way, we see, okay, it's the same entropy, but this doesn't tell everything about the difficulty in terms of recyclability. So different points need to be addressed, like, for instance, different structure, different linking between the materials. And an example of this is, for instance, multilayers versus monolayers. And this is not covered by just statistical entropy. And that's why we actually looked also at what they actually do in practice also quite often, looking at energy requirements which are needed to reduce entropy and combine these energy requirements to reduce the entropy, to actually decompose the product, the plastic bag filled with some objects, into or its components, being those two different components I explained before, or into its materials, or into its substances. And by combining the contribution at the entropy level and the energetic requirements, we actually formulated recyclability metrics, which could be used to quantify the recyclability of different plastic products, product mixtures, waste streams, etc. Now, this is quite an abstract example. We also have a more concrete example in the next slides. And that's something I wanted to show. So imagine now that you have a plastic waste collection bag, the PM+D bag, in which you have different types of components, and imagine that one of those components is, for instance, a plastic bottle. This plastic bottle, well, we now use levels defined in multi-level SEA, but we could also define levels differently, of course, and add more levels. Consists of different things like a bottle cap, bottle material, a label, and these things like the bottle cap are, for instance, made out of different substances. We apply that to a toy example of a plastic bag filled with plastic bottles, which differ in actually composition, mainly in the bottle label that is actually being made. All the rest is the same, so the bottle cap has the same composition, the bottle material has the same composition, but the labels are different. Namely, one bottle type has a monolayer label, other bottle type has a multi-layer label. And, well, looking at this, if we apply then the concept of this recyclability metric based on entropy, statistical entropy, and energy requirements, we can see that the bottles with a monolayer label are more easily recyclable than the bottles with multi-layer label, due to the fact that the multi-layers require more energy, although in terms of composition they are quite close to each other. So if you would look only at entropy, the differences would be quite small, while looking at the energy requirements which are needed and adding those into the picture will give a more truthful predictor or describer or quantification of the recyclability. So the conclusions of this conceptual introduction of the statistical entropy and extending this multi-level statistical entropy analysis with energy requirements to quantify the recyclability of plastic waste or plastics is that we can actually define such a recyclability metrics and as such quantify this recyclability of plastics. Now, future perspectives are actually to extend this framework to multiple levels, like for instance, multiple product systems, looking at their entropy at lower levels, like entropy of the polymers themselves, the molecular entropy, to say it like that, or also at distributions among society. How are these plastics or products distributed over society, in order to actually set up strategies for already designing products, for instance, or processes with recyclability or recycling in mind up front from a generic point of view. Could also use these concepts to develop optimal collection schemes, quantify the value of sorting or refining technologies, and develop eventually recyclability predictions. And that's something we want to also search for collaborations with other partners, maybe also within the capture network, to see how these metrics could be further developed and valorized in practical situations, in practical setting. So with that, I would like to thank you for your time and attention. And if you have any questions, please ask them now during this seminar, or you could also contact me or Peter Bille. Thank you very much.